All right, so our goal in this question is that we are given the graph of the original function, and they want us to sketch the graph of the derivative. So what I'm going to do is I'm going to label these. So this is the original, and I'm going to try to sketch the graph of the derivative. So mainly what they're asking you to do is remember what the relationships between a graph and its derivative are, and then apply those things to actually sketch the graph of the derivative. So here's what I would do first. All right. If you remember, if f of x has horizontal tangent lines, f prime of x equals 0. Because remember, the derivative tells you the slope of the original graph. So if the original graph has a slope of 0, then the derivative is going to be 0 there. So I would find those places first. So if you look right here, there's a horizontal tangent line right there, and there's a horizontal tangent line right there. Do not get tricked into taking the x-intercepts from the original and making them the x-intercepts of the derivative. Okay, don't get tricked. This one happens to be both, okay? But the only reason that I know my derivative equals 0 here and here is because I have horizontal tangent lines, which actually end up being a relative max and a relative min, right, of the original. So I'm going to say the original graph has horizontal tangent lines, the derivative equals 0, and that's happening at x equals 1 and x equals 3. So I can go over here to the graph of my derivative, and I can put x-intercepts at 1 and 3. Okay, so the first thing I would do if I were you when you're graphing a derivative from the original is I would look for horizontal tangent lines on the original and then make those x-intercepts on the derivative. Okay, now the next thing I have to do is, if these are x-intercepts, right, I have to figure out, these are the only place that this graph can cross the x-axis, all right? I have to figure out where the graph is between these x-intercepts and then like before it and after it, right? So if this is where I hit the x-axis, am I above or below the x-axis everywhere else? Okay, so let's go back. Here's the original. From -1 until 1, f of x is increasing. So the derivative is positive. So on the interval -1 to 1, the graph of the derivative needs to be above the x-axis because the original is increasing on that interval. So then the derivative graph needs to be positive. Now here's what I don't know. If it's positive, right, so let's go ahead and mark -1, all right? If it's positive that whole time, what's it doing though? So like that's positive the whole time, right? This is positive the whole time. Sorry, I went a little bit too far. This is positive that whole time, right? So I don't know if the derivative graph is increasing or decreasing. I just know it's positive. All right, so let's hold off on that. We haven't dealt with that yet. All right, let's keep going with those kind of intervals. Well, from -1 to 3, the original is decreasing. So the graph of the derivative is going to be negative on that interval. So maybe we can just like put some marks. So the original is positive. I'm sorry, the original is increasing on this -1 to 1. So my derivative needs to be positive. So like from here, it needs to be up here. And then from like, I'm sorry, I put -1. That's my bad. You're probably like shouting at the computer, right? And then from 1 to 3, which is over here, since the original is decreasing, the derivative should be negative. So over here, the graph is going to have to go negative between those two intervals, and then, or x values. And then lastly, the original is increasing from 3 until 5, right? Because it's increasing through there. And so if f of x is increasing, then the derivative is going to have to be positive again. So from 3 to 5, and then the graph's going to end because I don't have arrows at the end here. So from 3 to 5, it's going to go back up to being positive. All right, so we got the positives and negatives. We have the, and I'll put 5 here, we have the x-intercepts. All right, so the last thing we have to figure out is where does the derivative increase? Where does the derivative decrease? Okay, and where does the derivative have relative extrema? So where does it have relative maxes and mins? All right, we get that information from the second derivative, right? And now we don't have any information about the second derivative because we only have the original. But what we have to do to get this information is we have to study the concavity of the original. All right, so if we study the concavity of the original, we can see that the original is concave down, right? It's concave down right here. So the original is concave down on that interval. So the original is concave down from -1 to 2. If the original is concave down, then the derivative is decreasing. So now I know that the derivative is decreasing on that interval. So the derivative is decreasing on the interval -1 until I get to 2. All right, so I'm going to try to draw that part. From the beginning, from -1 to 1, I have to have a derivative that's positive. And then on most of that, well, actually all of that interval and then a little bit more, I have to make sure that I'm decreasing. So my derivative graph needs to be positive and decreasing from -1 to 1. So from -1 to 1, I have to be positive and decreasing. All right, so let's see here. I can start wherever I want as, with respect to y, but I need to be positive and I need to be decreasing until I get to here. So I'm actually until I get to 2, right? Because I have to keep decreasing. And then at 2, at 1, I go negative, right? Because it says right here, at 1, I go negative. And then I know that 1 is where it hits the x-axis. So one more time, I'm going to be positive and decreasing. I stay positive until I get to 1. I keep decreasing, and then at 1, I go below the x-axis, right? At 1, I go below the x-axis, but I keep decreasing until I get to 2. So right about here. All right, so just to go over it again. -1 to 1, my derivative should be positive, which it is. And actually, I might be a little too far over on that, but it's going to be dumb if I erase this. So just give me 1 second. I'll just do it like this. I just went a little bit too far, right past that. Okay, so from -1 until 1, my derivative needs to be positive, but on that interval, it also has to decrease, okay? Then at 1, my derivative needs to be 0, and then I still need to decrease from 1 to 2, which is what I'm doing right there. And because of this, from 1 to 2, my derivative graph has to be negative. So that's what's happening there. Okay? Now, if we go back to the graph of the original, you can see that I'm concave up this whole time. So I'm concave up there. Okay? So I'm going to go over here and write it. So f of x is concave up from 2, until 4, because they told me that this is the other inflection point. So the derivative graph is increasing on that interval. Okay, so now I know that my derivative graph needs to increase from 2 until 4. At that same time, my derivative has to be negative from 2 until 3. All right, so I know my derivative is 0 here. So I need to increase and be negative until I get to 3. I need to keep increasing until I get to 4. But at 3, my graph goes from being negative to positive. So it goes up like this until I get to 4. And I'm going to get rid of that other kind of thing here. I was just using that to kind of figure things out. Okay, now what happens? Well, at 4, I go back to being concave down. So f of x is concave down from 4 to 5. So the derivative needs to decrease on that interval. But from 3 to 5, my derivative graph needs to be positive. So I'm going to be positive and decreasing on that interval. So I'm positive, but I decrease. And that's actually not the best. I should probably try to round it earlier. So positive and decrease. Okay? You should notice that at my inflection points, so see how I went from concave down to concave up? This inflection point right here became a relative min of my derivative. And the inflection point right here, since I go from concave up to concave down, that became a relative max on the original. So this is a shaky drawing, but it's pretty much as good as I could do. And you know, it's pretty accurate, right? Okay, so let's try the other one. I'm going to pause the video, add another page here, and I'll scroll down and explain the next one to you. All right, so we're going to try to graph the derivative again. Hopefully you already tried this. I wouldn't watch the video and just copy what I do. Like, I would definitely try to do it first. All right. And again, this is probably going to be a little shaky, but we'll kind of just do our best to see what we got going on. All right, first of all, let's put some arrows here because that's, you know, just kind of assumed. So let's first figure out where the graph of the derivative is going to be equal to 0. So the graph of the derivative is equal to 0. So the graph of the derivative is equal to 0 when, or where, that's fine, the original has horizontal tangent lines. All right, so let's find those. There's a horizontal tangent line right there, and there's a horizontal tangent line right there, and there's a horizontal tangent line right there. So let's go ahead and plot those points. So the horizontal tangent lines on the original are the x-intercepts of the derivative. So here we go. -5 is an x-intercept. 0 is an x-intercept. And then there's another one at 3. 1, 2, 3. So there's my x-intercept. So I got that done. All right. Now let's do the whole increasing and decreasing thing and figure out where our derivative graph is positive and negative. So the original is increasing from -infinity until -5. It's then increasing again from 0 to 3. And so what that means is the derivative is positive on those intervals. So my derivative is going to be positive until I get to -5. So all the way till here, right? The derivative graph is going to be positive. And then my derivative graph has to go negative from -5 to 0 because the original is decreasing. So f of x is decreasing from -5 until 0, and then it's decreasing again from 3 to infinity. So that means that my derivative has to go negative on that interval. So from -5 to 0, my derivative graph is going to go negative. And then from 0 to 3, it's going to go back up to being positive because the original is increasing there. And then after 3 until infinity, my derivative graph, and these aren't asymptotes, I'm just kind of separating the graph out into intervals. And then let's see, so from 3 until infinity, my original graph is decreasing, so my derivative graph is going to go negative again. Okay, so we got the positives and negatives. Now let's deal with the concavity situation so that we can figure out where the derivative graph is increasing and decreasing. Okay, so f of x is concave down from negative infinity until negative 4 because they told us that this is an inflection point. So if the original is concave down on that interval and they told us that this was an inflection point, so it's also concave down from 1 to infinity, then that means the graph of the derivative is decreasing on that interval. So from negative infinity until negative 4, right, I have to decrease. So let's try to do that. I have to be positive and decreasing here. So positive and decreasing. Then I hit 0. And then I go negative at negative 5. That's right here. And then I still have to decrease till I get to negative 4. So I have to keep decreasing. Okay, so right about there. Now, according to the concavity, I go concave up here. So the original graph is concave up from negative 4 until 1. That's a 4, sorry. Negative 4 until 1. So that means that the graph of the derivative is increasing on that interval. So I need to increase until I get to 1. I have to stay negative though. Right here, I have to stay negative until I get to 0, but I need to increase. So negative and increasing till I get to here. I have to keep increasing until I get to 1, but now I'm allowed to go over the x-axis because at 0, right, my derivative graph goes positive again. So I'm up here. And then what happens next? I have to decrease from 1 until infinity. And I'm supposed to stay positive until I get to 3. So decrease and stay positive until I get to 3. Then after 3, I'm allowed to go negative, but I keep decreasing. And so it looks like that. Okay, so just to kind of recap, I would do it in this order. I would find the x-intercepts of my derivative first by looking where the original has horizontal tangent lines. And then I would break it into where the derivative is positive and where the derivative is negative based on where the original is increasing and decreasing. And then lastly, I would look where the original is concave up and down, and then that tells me where my derivative is decreasing and where it's increasing. Okay, so instead of just making like multiple videos, I'm just going to keep going, and I'm going to show you how to use the 3-part definition of continuity next. All right, so here's problem number 3, and it's asking you to use the 3-part definition of continuity to determine if this function is continuous at x equals 3. Now remember, the function doesn't have to be continuous everywhere. We don't care. We're just focusing on what's happening when x equals 3. If you remember, this is a piecewise function. And so what it says is, if you're going to plug in any values equal to 3 or less than 3, you have to evaluate those in the top equation. And if you want to plug in any numbers that are bigger than 3, they go into the bottom equation. The other thing I want you to realize is, when I say numbers bigger than 3 and less than 3, I don't necessarily mean the next integer. I literally mean bigger than 3 is 3.000001, right? And then 2.99999. So like when we're evaluating limits, that's where this is important. Okay, the inequalities over here. All right, so here's the 3-part definition of continuity. Make sure you remember it. Part 1, and actually here's what it says. F of x is continuous at x equals, and in this case 3, if, number 1, f of 3 exists. So this is just ensuring that at 3, the graph has a value. So if I go up to the piecewise function, I'm looking for the equal sign because I'm trying to actually plug in 3. So that means I'm going to use the top function since that's the one with the equal sign. So I would say f of 3 is equal to 3 squared plus 2 times 3. So that's going to be 9 plus 6 equals 15. So that means so far this function is continuous because f of 3 exists. Part 2, the limit as x approaches 3 of the function has to exist. All right, so now here's where the inequalities matter. All right, so for the limit to exist, we have to check from the left of 3 and the right of 3. So I'm going to kind of bring that over here to do it so that you can kind of see everything. So let's go ahead and check the limit from the left and the limit from the right. This is the function you would use when you're plugging in numbers that are smaller than 3, because it says less than or equal to 3. And it says use this bottom function if you're going to plug in numbers that are bigger than 3. All right, so here we go. So I'm going to do the limit as x approaches 3 from the left of f of x. So I'm going to plug 3 into the top function, right? So I'll do 3 squared, we already did this, but 2 times 3. So that's equal to 9 plus 6, or 15. So from the left, the graph is approaching 15. And we know it actually hits it, right? So from the left of 3, so here's 3, right? From the left of 3, the graph is going to go up towards 15, and it actually reaches it. And we know that from right there. Okay, so we'll say that this is 15, right? All right, now let's check to see what's happening from the right of 3. So the limit as x goes to 3 from the right of f of x is equal to, now this says if you're bigger than 3, if you're going to plug in numbers that are bigger than 3, then you have to use this function, right? If you really wanted to, so I don't want you to get confused here, and you're like, oh, I can't plug in 3 because it says it has to be bigger than 3. Yes, so technically what you're plugging in is 3.0000 forever and then a 1. You don't have a calculator, so you don't want to square that or multiply it by 2/3. So you can literally just plug in 3, okay? So we would go 2/3 times 3 squared plus 11. So let's see, that's 9, and then divided by 3 is 3. 3 times 2 is 6, plus 11, just make sure I'm doing this right, yep, is equal to 17. Okay, so that's the problem. From the right-hand side, this graph is actually approaching 17 instead of 15. So therefore, this is the symbol for therefore, you don't have to know that. The limit as x approaches 3 of f of x does not exist, since the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. So we can stop right now and we can say f of x is not continuous at x equals 3 because the limit, whoa, that was scary, the limit as x goes to 3 does not exist. Okay? Now, if the limit would have existed, then you would just have to check that f of 3 and the limit as x approaches 3 are the same. Okay? But this already failed, so we don't have to go any further. All right, so I'm going to go ahead and do number 4 with you, and then you should be good.